All right, so let's get started. Um, so today we're going to start with chapter 6. And so chapter 6, in this chapter, we are going to talk about an overview of the entire solar system. And then we will, towards the end of the chapter, we'll talk a little bit about the history of the solar system, like how the solar system came to be formed. Um, Very fascinating stuff. So this chapter, we are just getting a broad overview of the entire solar system. And then in the upcoming chapters, we will dive into each planet separately. Chapter 7 would be the study of the planet Earth, so our own planet. So that's not really astronomy, but it's still very, very important and very fascinating to understand our own planet before we start looking into other planets. Then we're going to talk about each of the planets separately. And we will end with the sun. Okay, so now we've discussed back in chapter 2 that our ancestors, when they looked at the sky, they were aware of the moon, the stars, 5 of the planets: Mercury, Venus, Mars, Jupiter, and Saturn. Uh, can you guess why just these 5? Why not the other planets? If you had to guess, why were they not aware of the other planets like Uranus and Neptune?
Oh, only thing I can think of is that they couldn't see. Well, I don't know if they could see them, but they couldn't see them.
Yeah, they're very, very difficult to see, very difficult to spot with the naked eye. Uranus and Neptune are almost impossible to see with the naked eye. I mean, with the naked eye, it's might be possible to see Uranus, but you have to be really know what you're looking for and where exactly to look. But that too, it's going to be extremely difficult. And Neptune is almost impossible to see without a telescope. So yeah, so that's the only reason. That's the reason why our ancestors were familiar with um, 5 planets: Mercury, Venus, Mars, Jupiter, and Saturn. And then they would often see comets in the sky. We're going to learn about comets in chapter 14. So comets appear as these long, wispy strands of light in the night sky. Um, and they move, they change position in the sky quite fast. So I mean, quite fast meaning night to night. So you won't see a comet moving on a given night, but if you track its position one night and then look for it 2 nights later, you'll see it's changed position quite a bit in the sky. And then, of course, they were familiar with shooting stars, right? Which are basically these flashes of light in the sky. Have both of you seen shooting stars in the sky?
No.
No? Rena, have you seen them?
No, I have not.
Oh, so you've missed. So shooting stars are actually quite familiar. So if you, I mean, you have to have a little bit of luck, and we're again going to learn about this in chapter 14. But if you're looking at the sky, you might see a streak of light suddenly go across the sky, and they are fairly often, and they do happen fairly often, and there are certain times of the year when they happen quite a lot. So those are called the meteor showers, and so they happen at fixed times during the year. So if you just look for when the next meteor shower is happening and go out to a dark spot at night, um, you might be able to see quite a few of them at night. So we are going to talk about that in chapter 14. But yeah, so that's something that people were familiar with in the old days. We will see later on that these shooting stars have absolutely nothing to do with stars. So it's just a misnomer because people had no idea what they were. So they called them shooting stars, but they're not stars at all. Okay. Um, so that's what our ancestors saw when they looked up at the skies at night. But they did not have any big understanding, any big picture understanding of how all of this worked. So they just saw that all this in the sky, but they had no idea why they were seeing all this or what exactly was going on. So there were all these wrong notions of what the universe and what the solar system looked like. We talked about that in chapter 2. There was this uh, geocentric model of the world, which Aristotle came up with, and that stuck around for 1500 years, as we've discussed, and it was Copernicus who changed our thinking on the solar system, and he was the one who introduced the heliocentric model. So we've talked about all this in chapter 2. Um, but basically, human knowledge of astronomy was revolutionized by the telescope. So the telescope really made a huge change to our understanding of astronomy. And so we've talked about all this. Galileo discovered the phases of Venus. He saw the 4 moons of Jupiter, as we've discussed in chapter 2. And all of that, as we've seen in chapter 2, completely changed our understanding of astronomy. And our knowledge of astronomy kept on improving with technological advances, and soon Saturn's rings were seen in 1659. The planet Uranus was discovered in 1781. Neptune was discovered in 1846, and then a bunch of moons and asteroids of planets were also discovered as telescope technology got more and more advanced. And nowadays telescope technology is very advanced, and we use not only visible light to study to do astronomy, but we use the entire electromagnetic spectrum, as I explained in chapter 5. We use radio waves, we use infrared, x-rays, gamma rays, everything in order to study astronomy. So there are a couple of pictures here. This picture is a telescope. It's a refracting telescope, which is not the good kind of telescope, which used to be once upon a time the largest telescope in the world, and it was about, I think, the size of a there's a human being here, a person here for scale. So it was the size of maybe a 5 or 6 story building, and it used to be the tallest telescope on the planet, but nowadays it's just a museum relic. And this is also a museum relic. This was the telescope which William Herschel used in 1781 to discover the planet Uranus. So this is also viewable in a museum in Germany. All right. So as we know now, so our knowledge of astronomy has improved tremendously over the years, and we have a lot of knowledge, a much clearer understanding of the solar system. So as we know now, our current solar system has one star. What is the name of that one star in our solar system?
Is it the sun?
Yes, of course, it's the sun. Very good. There are 8 planets. There are about 166 moons. The number of moons keeps changing as more and more moons are discovered. So 166 moons. How many moons does the planet Earth have?
I only know one.
Yes, that's the only one that the Earth has. Yeah, but other planets have more moons. Like Jupiter has around 67 moons. So in fact the outer planets have lots of moons. So there's 166 moons. There are 8 asteroids. Asteroids are basically large space rocks. So large space rocks are what asteroids are. And smaller space rocks are called meteoroids. So that's the difference between an asteroid and a meteoroid. So an asteroid is a large space rock. Large means more than 100 meters across. So more than 100 meters. And what is 100 meters? 1 meter is about 3 feet. So more than 100 meters means more than around 300 feet across. Um, that's an asteroid. And a meteoroid, my last bullet point here, is a space rock which is less than 100 meters across. So 100 meters is just arbitrarily chosen to be the demarcation between an asteroid and a meteoroid. And an asteroid is a large space rock, and a meteoroid is a small space rock, smaller space rock. So less than 100 meters across, we would call it a meteoroid, right? Okay, so there are asteroids can come in all sorts of sizes. You can have smaller ones, which are about 100 meters across, or you can have very large ones. So if they are larger than 300 kilometers in diameter, um, uh, then they're yeah, so those are considered the very large asteroids. And there are 8 large asteroids. So there are 8 of them which are that large, like 300 kilometers in diameter. And there are also 100 large Kuiper belt objects. So do you guys know what the Kuiper belt is?
No.
Rena, did you know what the Kuiper belt is?
No, I do not.
Okay, so you're going to learn a lot of things today in today's lecture. Okay, that's great. So the Kuiper belt is a region outside the orbit of Neptune where you have a large number of objects which are orbiting the sun, a large collection of objects which are orbiting the sun. Those objects are mostly made up of ice and some rock. So Pluto is one example of a Kuiper belt object. It's the largest Kuiper belt object. So there are around 100 large Kuiper belt objects, and by the definition of large is more than 300 kilometers across. So that's what we mean by large. So or since kilometers probably doesn't make that much sense to most of us, let me just convert that to miles. So 300 kilometers in miles is, yeah, about 180 186 miles. So uh, we call something a large asteroid or a large Kuiper belt object if it's more than 185 miles across. So that's what we call a large object. So there are 8 large asteroids that we know of and more than 100 large Kuiper belt objects. Okay, so here we are just taking an inventory of the entire solar system. Then there are tens of thousands of smaller asteroids, plenty of smaller asteroids. Um, then there are comets in the solar system, which are these objects that orbit the sun in highly eccentric orbits, and they are mostly made up of ice, and they're very interesting because when they show up in the sky, they show up in the sky because they're close to the sun, and so when they are when they get close to the sun, they develop this huge halo, and it's very fascinating. So you can see the comet with its halo going around the sun. So we'll talk about comets later on in this chapter and also in chapter 14. And then we talked about meteoroids. So meteoroids are basically the smaller space rocks, which are less than 100 meters across, right? So that's what we have in the solar system. So these are all the different things that we have in the solar system. All right. Now, okay. So we'll skip these 2 slides. We'll just skip this. Uh, here we are just talking about how do we measure the different properties of planets. So we're just going to skip that. All right. Now let's talk about a very important property of any object, which is called the density of the object. So the density is a measure of how compact that object is. So an example of a high density object would be iron. Iron has a very high density. A low density object would be cotton. Cotton has very low density. So density is a measure of how tightly packed an object is, right? Now, let's look at some examples of density. So iron has a density of around, actually, let me just define density first. Did we talk about density here? I didn't. Okay, so the definition of density is mass divided by, oh, here it is, okay. Yeah, this slide should have been first. All right, so let's talk about the definition of density. So the density is a measure of compactness, and the density is defined as the mass of the object divided by the volume of the object. Now let's just quickly remind ourselves what these 2 things mean. What does the mass of something mean?
How much matter something has?
Yes, exactly. How much matter something has, or how much stuff it is made up of, how much matter it has. And what does volume mean? What is the meaning of volume in plain English? Volume is how much space it takes up. space it takes up. So if you divide the mass of an object by the volume of the object, volume is how much space it takes up, then what you get is called the density of the object. And this funny looking symbol is the symbol, traditionally used symbol for density. It is a Greek letter. Do either of you know which Greek letter it is? Do you recognize this? Probably not. So this
Is
is
it
the,
is pi?
no, it's not pi. It's rho, Greek letter rho. So pi, which looks like this, is the Greek letter, is a Greek letter which stands for, it's their P, and rho is their R. So rho looks like this. Rho looks like a sort of weird curly P. So that's so it kind of looks like a P, but it's not exactly. The English P looks like this, and rho kind of is more curly. So rho is the Greek letter that's used as the symbol for density traditionally, and so rho is equal to mass divided by volume. So that's the definition of density, right? So mass is the amount of matter contained in an object, and volume is the amount of space taken up by an object. Okay, let's look at an example. What is the density of a block of mass 800 kgs that has a volume of 1000 meters cubed? So the density, we have to find the density of this. So let's go ahead and do that. Density equals mass divided by volume. So the mass, what should I plug in for the mass?
800.
Yes, 800 kgs. And what should I plug in for the volume?
1000.
1000. 1000 cubic meters. So volume is measured in cubic meters. That's the unit of volume. Okay. And so if you do 800 divided by 1000, you get 0.8 kgs per meter cubed or cubic meter. So this is either called meter cubed or cubic meter. So meters cubed, you can either call it that or you can call it cubic meters. Okay. So that's the unit of volume. Okay, a unit of volume that you are familiar with, that you use all the time, is liters or gallons. So 1 liter, let's see how many cubic meters it is. 1 liter in cubic meters is 0.0001 cubic meters. So all of you have heard of, both of you have heard of liters, right? So I'll just write this down. So units of volume. So one unit that we are going to be using in this course is cubic meters, which is also called meters cubed. And it's written like this, m to the power of 3. Another unit is liters, which you might be familiar with. So 1 liter is 0.001 cubic meters or meters cubed. And another unit of volume that you might also be familiar with is a gallon. And so what is 1 gallon? Let's see. So you can all find all of these very easily from Google by just typing 1 liter in gallons or 1 gallon in cubic meters. So 1 gallon is 0.0037 uh, cubic meters. So so this just gives you an idea of the unit of volume which we are going to use, the cubic meter. So you can also use liters or gallons, but it's more convenient for us to just use this particular unit, cubic meters, to estimate, to measure volume. Okay, so what we found here is the density in this problem. We divided mass by volume, and we got 0.8 kgs per meter cubed, and that's the answer. Let's try this problem. What is the density of sugar if zero point 0.5 kgs of sugar occupies 0.00315 cubic meters? So how would I do this one? What do I need to divide by what? So density is equal to mass divided by volume. So which one is the mass here?
The 1,000.
Mass would be measured in kilograms, right? Because
Okay.
it's,
Okay.
yeah. So which one is the volume? Which one is the mass?
800.
No, we are doing the first problem right now. This
Oh,
one.
okay.
Yeah. So we already finished this problem. So we are done with this, the
Oh,
one at the
okay.
bottom. Yeah. So we are doing the first one. So what is the mass here?
0.5.
Yeah, 0.5 kgs. And what is the volume?
0.003.5.
Yeah, 0.000315 meters cubed. And if you divide zero point 0.5 by 0.000315, let's see what we get. Just put that in a calculator. Um, zero point 0.5 divided by 0.000315. It gives us, if I did it correctly, it's 1587. Huh. Mass divided by volume. Let me just double check that. Oh, 150. See, did I do 0? Oh, 000, sorry. Yeah, so 1587. So it's 1587, approximately 1587 kgs per meter cubed. So that's the density of sugar. So is density clear? So if the density number is high, that means it's a very tightly packed material. And if the density number is low, then it's not a very tightly packed material. So which of these would you say has the highest density? So suppose we are talking about a solid and a liquid and a gas. So which of these would you say has the highest density, the solid or the liquid or the gas? Which is the densest? If you had to guess, which one would you say has the highest density? Just pick one at random. Which one do you think has the highest density?
The gas.
No, the gas actually has the lowest density. So density is how tightly packed it is. So the gas has the lowest density. The solid would have the highest density, right? So the solid has the highest density, and the gas has the lowest density. And the liquid would be somewhere in between. That makes sense? Okay, so the higher the density, the more compact, more tightly packed that material is. All right, so that is density. Now, okay, so you can probably do this. Which of these defines density? It's just mass divided by volume. So this is the correct answer, mass divided by volume. We just talked about that. All right, now uh, let us talk about the density of the Earth. So the density of the Earth is 5,500 kgs per meter cubed. Let's see how we would get this number, and then we will consider the consequences of this number. So um, let's calculate the density of the Earth. Density of the Earth. So density is mass divided by volume. Now, what is the mass of the Earth? So the mass of the Earth is 6 times 10 to the power of 24 kgs. That is the mass of the Earth. And what is the volume of the Earth? The volume of the Earth would mean the amount of space taken up by the Earth, right? So in order to find that, that's something that we have to calculate, and we'll do that really quick. But in order to find that, you need to know the formula for the volume of a sphere. So suppose you have a sphere. A sphere just means a large round shape. I mean, a round shape is what a sphere is. If the sphere has a radius r, then do either of you remember the formula for the volume of a sphere? Have you ever seen it?
A long time ago, I forgot.
Yeah, it's 4 divided by 3. So volume of a sphere, this is the formula. 4 divided by 3 multiplied by pi multiplied by the radius of the sphere cubed. So that is the formula for the volume of a sphere. Now, we can use this to calculate the volume of the Earth. We just need to plug in the radius of the Earth. So the radius of the Earth, what is the radius of the Earth? The radius of the Earth is 6,400 kilometers, or 6.4 times 10 to the power of 6 meters. So if you plug that into this formula for the volume of a sphere, this is what we get. 4/3 times pi times 6.4 times 10 to the power of 6. This has to be cubed. So all that we did here was, for r, we plugged in the radius of the Earth because we want to find the volume of the Earth. So if you do that, then let me just calculate that. For So you can just put this in a calculator and find it yourself. 4/3 times pi times 6.4 times 10 to the power of 6. That whole thing is cubed. So from a calculator, I get 1.09 times 10 to the power of 21 cubic meters is the volume of the Earth. So to find the density of the Earth, all I have to do is mass of the Earth, which I already know, divided by the volume of the Earth, which I just calculated. And let's see what answer we get. So the mass of the Earth is 6 times 10 to the power of 24. Volume of the Earth is 1.09 times 10 to the power of 21. This is kgs, this is meters cubed. And if you calculate this, or if you calculate this on a calculator, let's see what we get. 6 times 10 to the power of 24 divided by 1.09 times 10 to the power of 21. So that gives us this number, approximately 5,500 kgs per meter cubed. That is the density of the Earth. And so you can see that this number is not mysterious. It's just a consequence of mass divided by volume. So I took the mass of the Earth and I divided that by the volume of the Earth, which I calculated using this formula for the volume of a sphere. I know that the Earth is a sphere, and I just had to plug in the radius of the Earth, which I did. And I got this result that the density of the Earth is 5,500 kgs per meter cubed. Now, there are some interesting consequences of this number. The density of the Earth is 5,500 kgs per meter cubed. Let's compare that with the densities of certain materials. Now, water has a density of 1,000 kgs per meter cubed. That's the density of water, right? And rocks have a density of between 2,000 to 3,000 kgs per meter cubed. Um, I would say 2,000 to maybe 3,500 kgs per meter cubed would be the density of rocks. Probably need to update this. So the density of rocks is 2,000 to 3,500 kgs per meter cubed, right? And the density of water is 1,000 kgs per meter cubed. Now, suppose if I ask you, what is the Earth made of? So you might say that the Earth is made up of water and rock, right? So you have water in the oceans and the ground is rocks. So the Earth is probably just made up of water and rocks. But you can see just by looking at these numbers that that cannot be true, because if the Earth was mostly made up of rocks and water, then what would you expect the average density of the Earth to be? It would be, you would expect it to be close to these numbers, close to the density of either rock or water. But the density of the Earth is way higher. It's 5,500 kgs per meter cubed, much higher than the density of rocks or the density of water. So that tells us that the Earth cannot possibly be made up of the same kind of rocks that we see on the surface of the Earth. So there must be much more dense stuff in the interior of the Earth in order for the density to be this high. Do both of you understand that logic here? It's very similar to, suppose you go to a large classroom and you're told that the average score that the students have earned on a test that they've all taken is 80%, right? And so you look at a few of their test scores at random. You just look at maybe the kids seated in the front row, and you see that they've all done terribly. Like they've got 50%, 40%, 20%. So that would make you think that, oh, so there must be, if the average is that high, 80%, there must be some students who did really, really well. And the kids that are sitting in the front row are probably not the best students in the class. So just knowing that the average is so high would make you certain that there must be some students who have really done very well in the class in order for the average to be so high. And that's exactly what's happening with the Earth. So if we look at the stuff that the surface of the Earth is made up of, which is rocks and water, then the we would expect a much lower density for the Earth. But what we find for the density of the Earth is a much greater number, 5,500, which is much greater than the average density of either rocks or water. And so that convinces us that shows us that there must be really, really dense stuff in the interior of the Earth. And that's what we're going to learn in chapter 7. The interior of the Earth consists of much denser rock, and then the core of the Earth is metal, is iron and nickel. So the core of the Earth is very dense. It's made of metals. But it's really fascinating that you can just tell that just by looking at a couple of numbers. All right. I have another problem on density over here. Let's give this one a try. The density of iron is 7,900 kgs per meter cubed. What is the mass of a solid block of iron that has a volume of 1.5 cubic meters? So how would we do this problem? Density is just another application of density. You don't necessarily have to use rho. You can just write the whole word density if you like. Density is mass divided by volume. So in this problem, we are given the density. So you'd plug in 7,900, and that is equal to the mass divided by the volume. So the mass is not given. That's what we are solving for. What is the volume of this piece of iron?
1.5 cubic
Yeah,
meters.
it's 1.5 cubic meters. We don't need to write the units. So how do I solve for mass? What do I need to do to find the mass? So we just need to multiply both sides by 1.5, right, to isolate mass. So 7,900 times 1.5 is equal to mass divided by 1.5 times 1.5. So we just isolated the mass by multiplying both sides by 1.5. And if you work this out, 7,900 times 1.5 is 11,850. 11,850. Oh, you have to be careful about the units. So yeah, so this is not the correct answer. It has the wrong units. Which is the correct answer here? Which one has the correct units?
B.
Yes, B has the right units. It's kgs per meter cube. That's the unit of density. So this is the correct answer, B. So when you're doing problems, you have to be careful not just of the answer, but make sure that you're picking the one that has the right units. All right. Now, there's another thing about density, which I should mention here. Density has another very interesting application. So the density of water is 1,000 kgs per meter cubed in the SI units. Now, if you have a material that is denser than water, like iron, so density of iron, as we just saw, is 7,900 kgs per meter cubed. Now, if something is denser than water, what happens? What do you think happens if you put it in water? So suppose I have a container with some water and I put a block of iron in the water. Will it float or sink?
Sink.
Yes. In general, things that are denser than water, the things that have a higher density than water tend to sink, and things that have a lower density than water tend to float. So iron clearly has a higher density than water, so iron will always sink in water. Whereas wood, for example, the density of wood is only about, I think, 700 kgs per meter cubed. Um, so wood will float. So if something has a density less than the density of water, it will float in water. And if something has a density greater than the density of water, it will sink in water. So this explains a lot of different things. So um, the reason why a boat will float in water, even though the boat is very, very heavy, is so you might have thought about this question when you were young. So why is it that a rock which is so light will immediately sink in water, whereas a giant ship can float in water? The ship is much, much heavier than the rock. So how is it that a ship can float in water, whereas a rock will sink in water? The answer is that if you calculate the density of the rock, it will come to around 2000 or to 3000 kgs per meter cube, depending on what kind of rock it is. And so that density is greater than the density of water, so that rock will sink. Whereas if you calculate the density of a ship, the ship is shaped in such a way that its volume is very large. So the ship is shaped in a way so that it takes up a lot of space. So its volume is very large. So if you do mass divided by volume for a ship, because its volume is so large, its density will be less than the density of water. So you can take one of those huge, gigantic ships, those aircraft carriers, which can hold 5,000 people, and planes and ships, um, and calculate its average density by doing mass divided by volume. It's going to be less than the density of water, just because the volume is so large. So that is why ships can stay afloat, and ships and boats can stay afloat, whereas objects like rocks easily sink. That makes sense? Uh, the average density of human beings is about the density of water. And that is because we are mostly made of water, right? So the average density of human beings is very close to the density of water, which is 1000 kgs per meter cubed. Some people have a density greater than 1000 kgs per meter cubed, and some people have a density a little bit less than 1000 kgs per meter cubed. But on an average, human beings have a density which is very close to the density of water. Now, those people that have a density a little bit less than the density of water, like suppose a person has a density of around 900 kgs per meter cubed, will they find it easier or difficult or harder to float in water?
Easier?
Yes. So the more fat you have in your body, fat has a very low density. So the more fat somebody has in their body, the lower their average density is. So that's why people who are, you'll often find that people who are quite overweight don't have that much of trouble staying afloat in water. They find it easy to stay afloat in water. And that is because fat has a lower density than water. Um, Whereas people who have a lot of who have less fat in their bodies and have mostly bone and muscle, their average density will be greater than the density of water, because bones and muscles have a higher density than water. And so those people are the ones whose average density will be a little bit over 1000 kgs per meter cubed, and they will have a slightly harder time floating in water because their average density is greater than water. So the next time you're in a swimming pool, you can just check whether it's easy or difficult for you to just float. Like if you just take a breath and let yourself go, do you tend to just sink, or do you float up? So if you sink, that means your average density is greater than the density of water. And if you find that you can easily float, that means your average density is lower than the density of water. That makes sense? There is the Red Sea, no, the Dead Sea, sorry, not the Red Sea, the Dead Sea in Israel. You guys have heard of that, the Dead Sea?
Yes.
Yeah, in the Dead Sea, you can actually float very easily in the Dead Sea, and that is because the density of density of water in the Dead Sea is higher than usual. The density of water in the Dead Sea is something like, I think, 1024 or something kgs per meter cubed. So that is higher than the density of most human beings. So most people have no problem floating there in the Dead Sea at all. So almost everybody can very easily float in the Dead Sea. And I think that's also true to some extent for the Great Salt Lake in Utah. So that also has an unusually high density. The water over there has unusually high density. So anyway, so that's an interesting fact that objects float in water uh, depending on what their average density is. So if their density is greater than the density of water, they will sink. And if their density is less than the density of water, they will float up. That makes sense? All right. So
Yes.
that's density. Okay, now coming back to the solar system, let's talk about the layout of the solar system. So the solar system is absolutely huge by Earth standards, and but it's quite small by astronomical standards. So the width of the solar system would be, so this is kind of what the solar system looks like in this diagram. At the center you've got the sun, and then you've got the orbits of the planets, right? So the planets have more or less circular orbits, so those are the circles. And then the furthest planet is Neptune, and you can see it right here. And so you can see that beyond the orbit of Neptune you have this region where there are a bunch of objects which are orbiting the sun beyond the orbit of Neptune. What did we just call this region of objects that are orbiting the sun beyond the orbit of Neptune? This is something I asked you guys if you had heard of before.
It's
Begins
the
with a K.
I don't know how to
The
pronounce it.
Kuiper belt,
Yeah.
exactly. So that is the Kuiper belt. So you can see in this diagram that that region where you've got a bunch of stuff orbiting the sun, that's called the Kuiper belt. And so that is the solar system, right? So the Kuiper belt is basically the furthest out that you can go in the solar system. So this distance would be about 200 astronomical units. So this distance would be around 200 astronomical units. And that's more or less the size of the solar system, 200 astronomical units. 200 astronomical units, and can somebody remind me what was an astronomical unit again? We talked about that a lot in the earlier on in this course. What's the meaning of an astronomical unit, AU?
The distance from the Earth to the sun.
Yes, and how many miles is it? It's 93 million miles, right? So one astronomical unit is 93 million miles, which is a very large distance by our standards. But and so you can see that the entire size of the solar system is 200 astronomical units. And that is a very large distance by our standards, but it's nothing compared to a light year. So by astronomical standards, it's a very small distance. Okay, so we've seen that the paths of the planets are ellipses with the sun at one focus, which is basically Kepler's first law. And all of the orbits are approximately circular. Mercury's orbit is slightly less circular than the other ones. So Mercury's orbit is a little more elliptical than the other orbits. You can clearly see that the orbits are not evenly spaced. So you can see that the inner planets, the ones which are closer to the sun, have orbits which are pretty tightly packed, whereas the outer planets have orbits that are quite spaced out. And all the orbits lie in roughly the same plane. And what is the name of that plane in which all the orbits lie? So we've talked about that before. What's the name of the plane in which all the orbits lie? That is called the ecliptic, the plane of the ecliptic. So all of the planetary orbits lie more or less in the same plane, and that plane is called the plane of the ecliptic, right? And since the orbits lie in the same plane, you sometimes have something called a planetary alignment, which is absolutely a non-issue. It's just a coincidence. It does not bear any kind of significance at all. So when you have a planetary alignment, it means that you look in a certain direction of the sky and you see a lot of the planets all in the same direction of the sky. So for example, this particular alignment happened. One of them is recent and the other one is older. I've forgotten which is which. So I think it's probably this is the one that's older. So you can see the moon, and then you can see all these planets more or less in the same direction of the sky. And here also in this picture on the right, you can see Jupiter, Mercury, Venus, Saturn, Mars, all of these more or less in the same direction of the sky. So that just is bound to happen when all the planets are orbiting in the same plane. It might just appear to us that all of them are in the same direction of the sky. Like for example, in this picture, what's actually happening is we are on the Earth. So we are this blue dot over here, and to us, it just seems that all the planets are more or less in the same direction of the sky. And so, as I said, that's just a coincidence and that doesn't have any significance. But in astrology, they attach a lot of significance to this. But really, it's not a big deal at all. All right, now let's talk about the two types of planets there are in the solar system. So you have the terrestrial planets and you have the Jovian planets. So the terrestrial planets are called the inner planets also. That's another name for them. And the Jovian planets are also called the outer planets. And there's a clear distinction between the inner planets and the outer planets. So the inner planets are the ones up till Mars. So Mercury, Venus, Earth, and Mars are the four inner planets. So the inner planets are, so these guys are the inner planets. Mercury, Venus, Earth, and Mars. And Jupiter, Saturn, Uranus, and Neptune, these guys are the outer planets. Okay, so there's a clear distinction between inner and outer. The inner planets are small, dense, and solid. The outer planets are large, they have low density, and are mostly liquid and gas, mostly made up of liquid or gas. So that's the outer planets. So here is the differences between and another name for, yeah, I already mentioned this. Another name for the inner and the outer planets are terrestrial and Jovian. So here are some differences between the terrestrial planets, which also means the inner planets, and the Jovian planets, which also means the outer planets. Okay, so the terrestrial planets are small and dense. The Jovians are huge and gaseous. And the Jovian planets are mostly made up of hydrogen and helium, which you don't see on the terrestrial planets at all. You don't see the light gases, hydrogen and helium, anywhere on the terrestrial planets. Um, the terrestrial planets are closer to each other, so their orbits are very close to each other relatively, whereas the Jovian planets are very widely spaced. So their orbits are very, very far away from each other. And you can see that very clearly in this diagram. So you can see how closely packed the orbits of the inner planets are and how spaced out the orbits of the outer planets are. Then another difference between them is that terrestrial planets have weak magnetic fields. We'll learn about magnetic fields in the next chapter, whereas the Jovian planets have very strong magnetic fields. So you're going to see that Jupiter and Saturn have really strong magnetic fields. And another difference between the terrestrial and the Jovian planets is that all the Jovian planets have rings, which the terrestrial planets don't. So the Earth doesn't have any rings, or neither does Mars or Mercury or Venus. But Jupiter and Saturn and Uranus and Neptune all have rings. The most spectacular ring system, of course, is Saturn. All right. Now, there are many differences among the terrestrial planets themselves. So the terrestrial planets are Mercury, Venus, Earth, and Mars. So there are many differences among them. So they are put in a group, but there are still many differences among them. So all four of them have atmospheres, but the atmospheres of these planets are very, very different from each other. So, for example, Mercury has almost no atmosphere at all, whereas Venus has a very thick, extremely dense atmosphere. We are going to see that when we get to these chapters. Um, the Earth has an atmosphere, but which is the one that we are familiar with. Mars also has an atmosphere, but it's much less dense than the Earth's atmosphere. Okay, so all the atmospheres of the planets, of the four terrestrial planets, are very different from one another. Then Earth and Mars spin roughly at the same rate. Oh, the Earth is the only one that has liquid water and oxygen in its atmosphere. So the Earth is the only planet in the solar system where you have water in liquid form. You have water in ice form and water vapor form on other planets and moons, but Earth is the only place in the entire solar system where you have water in the form of liquid. All right. Then Earth and Mars spin at roughly the same rate, which is 24 hours taken for a single spin, whereas Mercury and Venus both take months to rotate once. So they rotate much slower than the Earth does. Okay, then Earth and Mars have moons, but Mercury and Venus don't have moons. And then Earth and Mercury have magnetic fields of very different strengths. Mercury has an extremely weak magnetic field, but Earth has a much stronger magnetic field than Mercury. Venus and Mars don't have magnetic fields at all, right? So you can see there are many differences between the terrestrial planets, even though they're grouped together. Now, why are they called terrestrial planets? Do you guys know what this word means? So why are the inner planets also called terrestrial planets? What does the word terrestrial mean? So the word terrestrial means like the earth. Terra is the Latin word for ground or the earth. So terrestrial planets are the planets which are like the earth in the sense that they have a solid surface that you can stand on. So these are four planets that have solid surfaces and you can stand on these surfaces. It's not possible to stand on the surface of Jupiter or stand on the surface of Saturn because these planets don't have any solid surface. They are mostly made up of liquid and gas. But you can stand on Mars, you can stand on Venus, you can stand on Mercury or the Earth. So that's why these planets are called terrestrial planets because they've got solid surfaces. All right. Now we talked about the planets. What is interplanetary matter? So these are the countless chunks of rock and ice that abound in the solar system and are mostly orbiting the sun. So that is what interplanetary matter is. Uh, Interplanetary matter could be very large objects, large space rocks, like the large asteroids and the large members of the Kuiper belt that we've talked about earlier. They could also be smaller pieces of ice or rock. So the smaller comets or even the smaller meteoroids. And then you can also have interplanetary matter purely in the form of dust, interplanetary dust. So we'll see later on at the end of this chapter that you have a lot of dust spread around in space, plenty of dust particles which are spread around in space. Okay, so that's also interplanetary matter. All right, now let's talk about asteroids and meteoroids. So asteroids are these are objects which are generally rocky in composition. Okay, so let me just explain one thing here. So we are all in astronomy, we'll often talk about things which are rocky or icy. Rocky means mostly made up of ice, mostly made up of rock. Oops. Mostly made of rock. And I'm putting rock in quotes over here because it's not necessarily the same rocks that we see on the Earth, but stuff which has composition similar to Earth rocks. So Earth rock is made up of chemicals which are called silicates. So stuff that is made up of silicate material. So stuff that is similar to rock. So that is a rocky substance, which is made up of material which we would identify as rock on the Earth. And what about icy? Icy means stuff that's mostly made up of ice. And once again, I'm putting ice in quotes because we are only familiar with one kind of ice on the earth, which is frozen water. But you can have ices of different things. You might have seen dry ice in the grocery stores. Dry ice is basically a different type of ice. It's frozen carbon dioxide gas. There can also be other types of ice. Like many gases, when you cool them up sufficiently, they turn into solid ice. Like you can have ammonia ice, ammonium hydrosulfide ice. So when I say ice in astronomy, it's not necessarily just water ice, but many other kinds of ices as well. So when we say that an object is mostly icy, it means that it's mostly made up of things which we call ice. And if I say that an object is rocky, then it's made up mostly of things which we would identify as rock. So that's the difference between rocky and icy. So we were talking about asteroids here. Asteroids are generally rocky in composition. So now you understand what that means. It means that they are mostly made up of rocky material, things that we identify as rocks. So we've talked about this second point before. So anything larger than 100 meters across is called an asteroid, and anything smaller than that is called a meteoroid. So that just means that asteroids are the larger space rocks and meteoroids are the smaller space rocks, and the point of demarcation, point of separation between them is generally taken to be 100 meters. So if it's more than 100 meters across, we call it an asteroid. If it's less than 100 meters across, we call it a meteoroid. Now, asteroids are very crucial to our understanding of the solar system because they are absolutely ancient material that has not changed since the beginning of the solar system. So asteroids have been around since the very beginning of the solar system, which we'll see at the end of this chapter. So they contain absolutely crucial information about the origin of the solar system, and so they are very useful to us. So when asteroids hit the earth, astronomers are very happy to get their hands on them and study them and find out what they're made of and what their dates, how old they are. We have ways of doing that, and that gives us crucial information about how the solar system originated. One of the things that we found from studying asteroids is that some of them, there's no asteroids that are more than approximately 4.5 billion years old. Not one asteroid has been found that's more than 4.5 billion years old. So what does that tell us about the solar system?
How old the solar system is?
Yes, exactly. So that's one piece of evidence that the solar system is about 4.5 billion years old. I mean, there's not been one asteroid which is older than that. So we've been studying asteroids for a very long time. Um, so since asteroids have been around since the beginning of the solar system, that tells us, so they contain crucial information about the very early history of the solar system. And we're going to talk about the history of the solar system at the end of this chapter. Um, yeah, and they often show up on the Earth when they hit the Earth in the form of meteoroids. So when meteoroids hit the Earth, um, they are called meteorites. So there's another piece of terminology here. So let me just make this really clear. So there are three terms that I defined: asteroids, meteoroids, and meteorites. So that's a new term that I just used over here, meteorites. I didn't say meteoroids, I said meteorites. So let's make sure we understand what the difference between these is. So what was the difference between asteroids and meteoroids, the first two things that I just wrote here?
You said the asteroid. Anything larger than 100 meters across is called an
Yes,
asteroid.
exactly. So the larger space rocks, so larger than 100 meters. And meteoroids are smaller than 100 meters. Okay, what are meteorites with a T? Meteorites are, so suppose a space rock comes in and hits the Earth, right? Now it's not so easy for a space rock to come down and hit the Earth's surface, because the moment it enters the Earth's atmosphere, since it's moving very, very, very fast, as it moves through the atmosphere, the friction with the atmosphere, friction with the air, causes it to heat up, and so it starts burning, right? And so it might often happen that they might completely burn up in the atmosphere and not even reach the surface of the Earth. So in that case, nothing is going to hit the surface of the Earth. But a larger meteoroid might burn up to some extent, but then there might still be some meteoroid left which crashes onto the Earth. So the stuff that actually hits the Earth is called a meteorite. So this is something that has actually hit the Earth's surface, actually landed on the Earth's surface. Remember that not all meteoroids entering the Earth's surface can survive the passing through the atmosphere. Like, they might just burn up. But some of them might survive that, and then they might land on the Earth's surface. And when they land on the Earth's surface, they're called meteorites, right? So meteorites are space rocks that have made it through the atmosphere and have landed on the surface. All right. So that also explains what shooting stars are. So when a space rock, a meteoroid, uh, enters the Earth's atmosphere, as it's moving through the atmosphere, it starts burning, right? So if you happen to be looking in that direction of the sky, you will see this streak of light go across the sky. It's basically that meteoroid which is burning in the atmosphere, streaking past, right? So that is what a shooting star is. So it has absolutely nothing to do with stars. It just appears to the sky as a as a streak of light going across the sky, right? So that's what a shooting star is. So a shooting star is just a burning meteoroid. And if this meteoroid uh, burns up in the atmosphere, then that's the end of the story. But if it does not burn up in the atmosphere and manages to crash into the Earth, what do we call it then?
Meteorite.
Yeah, that's what a meteorite is. Very good. Okay. All right, so let's get started. So we talked about asteroids and meteoroids, and hopefully all this terminology is clear. What is an asteroid? What is a meteoroid? What is a meteorite? And what is a shooting star? So we will cover this again when we get to chapter 14, which is about all this stuff. But all right, so we talked about that. Another thing that we see in the solar system are comets. So comets are objects which are more icy than rocky. So they're made of more icy materials, materials which resemble ice rather than materials that resemble rocks. So they can be 1 to 10 kilometers in range. And comets, also like asteroids, represent truly ancient material. So the vast majority of the comets have not changed since they formed with the rest of the solar system. So they are absolutely ancient materials. They're made of very, very ancient material. And comets appear in the sky like this. So you can see this tail of the comet. So you can see, in fact, two tails of this comet. Oh, sorry. Thank you. Forgot to share my screen. Thanks for pointing that out. Um, okay, yeah. Thanks for pointing that out. So what I was saying is that comets are more icy than rocky. Their diameters can be 1 to 10 kilometers. So they can be small or they can be very large. and their chemical makeup is similar to icy moons of the outer planets. So this bullet point is not going to make that much sense because we haven't talked about the outer planets' moons yet, but they're mostly made up of icy material, is what the comets are. And as I was saying, they are made of truly ancient material. So the comets have not changed since they formed together with the rest of the solar system 4.5 billion years ago. So they have been around for a very, very long time. And um, comets, the spectacular thing about comets is that you can see the tails of the comets. So here's one comet, and you can see that it has two tails. You can see one tail right here and another tail right here. Um, One of them is called the dust tail and the other one is called the ion tail. We are going to learn about this later on. But basically, why does the comet have tails? And also, as the comet gets closer and closer to the sun, the tail gets even larger. So, but then as the comet starts moving away from the sun, the tail gets smaller and smaller, and then gradually the comet disappears. So why does the comet have tails? That is because the comet is mostly made up of icy materials, and when icy materials get closer to the sun, instead of melting, the ice just turns into a gas. So that process is called sublimation. So the ice just turns into a gas, and so the gas is what you can see. That's why it develops a tail. And as it gets closer and closer to the sun, more ice sublimates into gas, and so the tail gets larger. So um, so that's a comet, and we're going to talk about comets in chapter 14 as well. Okay, yeah. So that's comets. Then um, we talked about the Kuiper belt. So the Kuiper belt is located beyond the outermost Jovian planets. So now you know what the Jovian planets are. So the planets, the four outer planets are called the Jovian planets. The outermost Jovian planet is Neptune. So beyond the orbit of Neptune, you have the Kuiper belt. And the Kuiper belt is a region where you have mostly icy comet-like objects which are orbiting the sun. And some of them are small, so their size can be less than 1 kilometer. And some of them can be very large, so their size can be more than 1,000 kilometers. So most of these objects have been discovered recently. So previously people didn't even know about the Kuiper belt, but most of the objects in the Kuiper belt have been discovered recently. The only one object in the Kuiper belt that was known for a long time was Pluto. And we thought that Pluto was a planet. We classified Pluto as a planet. But after a bunch of Kuiper belt objects were discovered, it just didn't make sense to consider Pluto a planet anymore after that. So in 2006, Pluto was demoted from planet to dwarf planet. Um, and that is the new designation of Pluto. So nowadays it's called a dwarf planet. Uh, were you guys aware that Pluto was demoted from a planet to a dwarf planet and is no longer considered a planet?
I was not aware.
Okay, yeah. So did you think of Pluto as a planet?
I did.
Okay, yeah. So that's what we grew up thinking. I mean, older people like Rena and myself, probably not Adriana. So we always thought of Pluto as a planet, but in 2006, uh, uh, Pluto was um, demoted, and it's no longer considered a planet since 2006. So the solar system only has 8 planets, and Neptune is the outermost planet. So I'm just going to briefly talk about why Pluto was demoted and why it's not considered a planet, and what are the criteria for a planet. um, this is not in chapter 6. So this is in your book somewhere. I've forgotten which chapter it's in, but it's not in chapter 6. However, I teach it as part of chapter 6, so it might be on quizzes and exams. I might ask you this. So please pay attention to this portion. So what is the definition of a planet now? So this definition was arrived upon in 2006. So there are 3 criteria that an object needs to meet in order to be considered a planet. The first one is that it must be um, wait a second, massive enough to be spherical. Oh, actually, we'll do this one first. So the first criterion is that it must orbit the sun. So anything that orbits the sun is, I mean, so orbiting the sun is a major requirement. It's the first requirement in order for something to be considered a planet. The second requirement is that it must be massive enough to be spherical. So let me explain what this means. So you know what spherical means, right? So spherical means round. Where when is an object, why are most objects that we see, like the moon and the earth and Mercury and Venus, so most Mars, they mostly look spherical. So why are they spherical? The reason is gravity. So you know that gravity tends to pull everything inwards, right? And the more mass you have, the more gravity something has. So if an object is very massive, if it has a lot of mass, then its gravity is very strong, and gravity likes to pull everything towards the common center. And that is why the object becomes spherical. Because if you have an object that's not completely spherical, like if it has an edge or a corner like this, then gravity will just pull this down, right? So it's not going to allow it to have any edges or corners or anything sticking out. If it has a strong enough gravity, it will just turn into a sphere, right? A sphere is the most compact shape. So, however, if an object is not massive enough, then it has no reason to be spherical. So, if you look at pictures of asteroids, most of the asteroids are not massive enough to be spherical. So, asteroids have all possible shapes. So they mostly look like potatoes. They have all possible shapes. It's only when objects are massive enough that they assume a spherical shape. So that is the second requirement. The object has to be massive enough to be spherical, right? Or in other words, it has to have so much mass that its gravity is strong enough that it can only be maintain a spherical shape. Okay. The third requirement is that it must have cleared out its neighborhood. What does that mean? So consider the solar system. So here is the sun, and here is the first planet, Mercury, that's orbiting the sun, right? And here is the second planet, Venus, that's orbiting the sun. And I'll draw one more. Here is the Earth, third planet, that's orbiting the sun. Now, out at the distance of Mercury, the first planet, you don't see any other large object orbiting the sun at that distance. So you don't see another planet like Mercury orbiting at the same distance. You don't. So out at the distance of out at the orbit of Mercury, there is only one thing, Mercury, right? Out at the orbit of Venus, there is only one planet, Venus, orbiting. Out at the distance of Earth, there is only one planet, Earth, which is orbiting. So you don't see any other large object orbiting at that distance. There's a reason for this. Once upon a time, you had, and we're going to talk about the solar system history in the next class, but once upon a time, you had plenty of objects which were orbiting the sun everywhere. So you might easily have had multiple large objects which are orbiting out at the distance of the Earth. So it's quite possible that there were multiple objects, Earth-like objects orbiting over here, multiple Venus-like objects orbiting over here at that distance. So you had a bunch of stuff that are orbiting the sun all over the place. But these objects would often collide with each other. And when they collided, whichever was stronger would survive, the other one would be shattered and or absorbed into the stronger one, right? The bigger one. So there was this constant competition among all the objects which were orbiting the sun. And then what eventually ended up happening was that at a given distance from the sun, like the Earth's distance from the sun, all of these other ones got kicked out. I mean, got just disappeared. So how did they disappear? They either got absorbed into the Earth, or they got kicked out of this orbit, or they got just pulverized by the Earth in a collision with the Earth. So the Earth was the last man standing, basically. So the Earth is the only one that managed to survive managed to stay in orbit at this distance from the sun. Same thing happened with Venus. So once upon a time, there was a lot of things which were orbiting at the distance of Venus, but Venus managed to just get rid of them, either by absorbing them or by just kicking them out of the orbit or by slamming into them and just pulverizing them, right? So as a result of that, Venus is the last man standing at that particular distance. So all these other ones, oops, just disappeared, and the only thing that was left at the distance of Venus was the planet Venus itself. And the same thing happened with planet Mercury. So this process is called clearing out its neighborhood. So all the planets have cleared out their respective neighborhoods, and that is why you only have one planet at that particular distance from the sun, because everything else has been kicked out of that orbit. So that is the third requirement for being called a planet. An object must have cleared out its neighborhood. So these are the three requirements in order for an object to qualify as a planet. Now, let us look at Pluto. Uh, would you say that Pluto orbits the sun?
Mm.
The answer is yes, it does orbit the sun. So Pluto meets the first requirement. Is Pluto massive enough to be spherical? Pluto is actually spherical, so it does meet the second requirement as well. However, it does not meet the third requirement because Pluto has not cleared out its neighborhood. Out at the distance of Pluto, so very, very far away, out at the distance of Pluto, you have a bunch of other objects which are more or less the same, which are comparable in size to Pluto, and also a bunch of objects which are much smaller, and that is called the Kuiper belt. So there is a bunch of objects which are um, in the Kuiper belt orbiting at the same distance as Pluto, which have not which are comparable in size to Pluto, right? So Pluto clearly has not cleared out its neighborhood, and that is why it does not meet the third requirement, and so it's not considered a planet. There is a name for objects which meet the first two requirements but don't meet the third requirement, and that is called dwarf planet. So Pluto is considered a dwarf planet. There are some other dwarf planets as well. So in between the orbits of Mars and Jupiter, so if this is the sun and this is the orbit of Mars and this is the orbit of Jupiter, so this is Mars and this is Jupiter, there happens to be a region of large region of asteroids. I'll just draw them with a different color. There happens to be a large region of asteroids which are orbiting over here between the orbits of Mars and Jupiter. So this is called the asteroid belt. Again, we'll study this in chapter 14. So this region of asteroids between Mars and Jupiter is called the asteroid belt. And there are some large asteroids in this asteroid belt, which were also once considered to be planets, but it was then realized that there are so many of them at the same orbit. So the largest ones in the asteroid belt are also called dwarf planets. So Ceres is an example of another dwarf planet which lives in the asteroid belt. It's basically a very large asteroid in the asteroid belt. So Pluto, Ceres, so these are all examples of dwarf planets. So dwarf planets examples are Pluto, Ceres, Vesta. So these are all examples of dwarf planets. So everybody clear about what the definition of a planet is and which requirement Pluto does not meet? So what are the three requirements and which one does Pluto not meet? Is that clear?
Yes.
Okay, so that is why Pluto is not considered a planet, because it does not meet the third requirement. And if you watch this video that's linked over here, you can see the same thing. It's explained really nicely. So which of the following is a reason for declassifying Pluto as a planet? The correct answer is, uh, which one is the correct answer here?
C.
Yes, C is the correct answer. Pluto has not cleared out its neighborhood. All right. So we have more or less covered this chapter. It's one of our shorter chapters. The only thing that's left in this chapter is the history of the solar system. We talked about what the composition of the solar system is in the last class. We talked about all the different. We talked about the two types of planets, the inner planets and the outer planets. Then we talked about things which are not planets, like the asteroids and comets. We talked about the asteroid belt and the Kuiper belt, and then we also talked about why Pluto is not considered a planet now, why it was demoted. So we discussed all that. Now, the last thing that we'll talk about is the origin of the solar system. Now, one thing about the solar system is that it shows a high degree of order. So it's not just some random stuff that's floating around the sun. It shows a high degree of order, and so the organization of things in the solar system seems to indicate that there might be a single origin for the entire solar system. It's not just that there was some star, the sun, and it just aggregated stuff, and that's why you have stuff orbiting the sun. It seems like the whole solar system sort of came into existence together. So there might be a common origin for the entire solar system. So I'll explain what I mean by high degree of order in the solar system. Uh, so the things that we see are that seem to give us a clue that the solar system had a common history, is that each planet is relatively isolated in space. So we talked about that in the last class. We mentioned how um, each planet is at the place where each planet is orbiting the sun, you only have that one planet. You don't have a bunch of other things orbiting at that same distance. So we call this clearing out the neighborhood. So we see that each planet is relatively isolated in space. Then we find that the orbits of the planets are all nearly circular, right? Um, Orbits of the planets all lie in nearly the same plane. Then we find that the sense in which the planets are rotating uh, around the sun is the same sense in which the sun is spinning. So the sun is spinning in a certain way, and the planets are all orbiting the sun in the same sense, right? Um, right. Then another thing that we find is that if you look at what the planets are made of, you find that there is definitely a progression over there. So you find that Mercury is made up of metals, mostly a lot of metal, and rock, but more metal than rock. The Earth is mostly made up of rock and a little bit of metal. And then as you go further and further out, you find that the planets are made up of mostly gas and ice and stuff like that. So there is clear differentiation among the planets. What does differentiation mean? Differentiation means that there is an order in which, so if you look at the stuff that the planets are made up of, there is definitely it's not just that all planets are just made up of random stuff. So closer to the sun, you have Mercury, which has a lot of metal, little bit of rock. Then you have Earth, Mars, and Venus, which have a lot of rock and some metal. And then as you go further out, you find that planets are made up of gas and ice. So that is differentiation. So that means there is definitely some kind of order among the materials that are making up the planets. And then finally, we have these asteroids, which are very old, and they exhibit a range of properties which are not seen in the inner and outer planets or in their moons. So you have these asteroids. So looking at all of this together seems to indicate that there might be some common origin for the entire solar system, right? It's not just that a bunch of stuff, random stuff is orbiting around the sun. So there seems to be some common origin for the solar system. Okay, now, so this is something that people have wondered about for a long time, how the solar system came into existence. And so that's what I'm going to discuss now. So the earliest theory for the origin of the solar system is called the nebular theory, which people thought about since the 1700s, late 1700s, I think. So I think it was a person named Laplace, a mathematician, who came up with the nebular theory. So the nebular theory for the origin of the solar system goes like this. So it says that in the very beginning, there was a dusty interstellar cloud. So that means there was this huge, huge cloud of gas and dust, right? Huge cloud of gas and dust, which was called a nebula. And that was very, very large, much larger than the size of the solar system. So the size of this cloud of gas and dust would be something like 100,000 astronomical units. And to compare that, to get an idea of how large that is, the size of the solar system right now, like if you look at the size of the solar system, um, so you have the sun over here, and then you have the outermost planet and the Kuiper belt. So the size of the solar system would be around 200 astronomical units. So the size of the solar system is only 200 astronomical units, but we are talking about a huge cloud of gas and dust, which was 100,000 astronomical unit, and that was the starting point of our solar system. So this cloud of gas and dust was um, there by itself for a long time, but for some reason it became unstable. So what does that mean? So whenever you've got a huge cloud of gas and dust, there are essentially two forces acting on that cloud. So one is gravity, which is trying to pull everything inwards, right, and make everything collapse. And the other one is a sort of outward pressure. So when you try to scrunch things together, then they sort of push outwards and create pressure. So there was that outward push of pressure, and then their inward pull of gravity, right? And so these two were more or less balanced for our cloud. But for some reason, our cloud became unstable. And once it becomes unstable, it just starts collapsing under gravity. So you have this huge cloud of gas and dust. And once it becomes unstable, the whole thing starts falling inwards because gravity attracts everything. So the whole cloud starts collapsing inwards. All right. So as this cloud collapses, a couple of things happen. One is the cloud might have had some kind of rotation. So it would be very surprising if our cloud was not rotating at all. So in the very beginning, it might have had a little bit of rotation going on. So it might have been rotating very slowly. But as it collapsed, the rotation started speeding up. So that is something that you are already familiar with. You know that I'll show you this example. Let me just make sure that the sharing is working. Oh, did I not share my screen? Sorry about that. Okay. Um, let me just share the screen. So I'm essentially just following the PowerPoint, but I'll just share the screen as well. Sorry about that. I didn't see that my screen is not being shared. Okay. All right. So this is basically what I was talking about. I'll just start talking about the nebular theory again because I just realized that my screen was not being shared. Um, so anyway, so there was in the beginning there was a, let me just, so the nebular theory of the origin of the solar system states that in the very beginning you had this huge interstellar cloud of gas and dust, which was called the nebula. And the size of this cloud was extremely, extremely large, 100,000 astronomical units. And I was just telling you that if you compare that with the size of the solar system, then the size of the solar system is only about 200 astronomical units. So it's only 200 astronomical units is the size of our solar system. So we are talking about a cloud of gas and dust, which was much larger than the current size of the solar system. So at first, this cloud was balanced because the inward pull of gravity was balanced by the outward push of pressure inside the cloud. But for some reason, it got unstable, and then it started contracting. So gravity won over, and the cloud started contracting, and it started falling inwards. Everything started falling inwards. All right. So as this cloud continued to collapse, what happened was that it started rotating faster. So why would it start rotating faster if it as it collapses? The reason is because of something called conservation of angular momentum. It's a physics thing, conservation of angular momentum, and you might be. It's something that you're probably already familiar with. So if you watch this video, I'll just make sure that my okay. So let's watch this video. So you can see how she speeds up tremendously as a result of bringing her arms and legs in closer. So whenever things get, if something is spinning and it becomes more compact by just bringing, like like in her case, she's bringing her arms and legs closer and getting more compact, and so it'll spin faster, right? So that's something that you might be familiar with, and that's you might have also tested this out on a swivel chair. So if you have a nice swivel chair, you can just spread out your arms and legs and then give yourself a spin, and then just bring your arms and legs as close to yourself as possible. You will find that you automatically start spinning faster. So the same thing happens to our collapsing cloud. So as it collapses, it starts rotating faster and faster, right? And the more it collapses, the faster it starts to rotate. So the contraction of the cloud and the rapid rotation also does something else. It makes our cloud, which we're also calling the nebula, it makes it flatten like a pancake. So the cloud assumes a flattened shape, which kind of looks like this. So at first, the cloud might have been this huge blob, but as it contracts and spins faster and faster, the contraction and the rotation makes the cloud assume a flattened pancake-like shape, right? Okay, the densest part of the cloud is the center of the cloud. So that is where, because gravity is trying to bring all the matter concentrated at the center, so the densest part of the cloud is the center of the cloud, right? And eventually, that dense part of the cloud, the densest center of the cloud, will eventually turn into what is now the sun. But we'll see how that happens. And the rest of the cloud will turn into the planets. So, but we're going to talk about how that happens. Here is an artist's conception of what the solar nebula might have looked like, what the nebula might have looked like. You can see all the clouds of all the gas and the dust over here. Okay, so our cloud is shrinking, 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 shrinking. And by the time it shrinks to something like a few hundred astronomical units, the solar nebula forms a extended rotating disk. So we just talked about that. It's now looks like a disk, right? And it's shrunk to about 100,000, 100 astronomical units, which is the current size of the solar system. So the central part of this disk eventually becomes the sun, right? And the remaining part forms clumps, which eventually become the planets. And that is the nebular theory. So the nebular theory says that everything started out as this huge, gigantic cloud of gas and dust. And then the cloud became unstable for some reason. It started collapsing on its own weight, collapsing as a result of its own weight. And as it collapsed, it started spinning faster and faster. And we saw that that's bound to happen. That's just a law of physics. When something gets more compact, if it's already spinning, it starts spinning faster. And the contraction and also the spin make the cloud assume a flattened shape like a pancake. And so we end up with a rapidly spinning disk of matter. The densest part of the matter is the densest part of the disk is at its center. And then the really dense central part of the disk turns into the sun, and the other parts of the spinning cloud turn into the planets. Now, this was the nebular theory up till here. However, there was one problem with this nebular theory, which is how do the nebular theory says that the remaining gas forms clumps, which eventually become the planets. But from computer simulations, we know that a hot gas does not really form clumps. I mean, even if it does, those clumps just dissipate away. So it by itself, the nebular theory cannot explain how the planets formed, because a hot gas does not just spontaneously form clumps of matter and turn into planets. So that's not clear from the nebular theory. And so this was not understood for quite a while until people figured out the condensation theory. The condensation theory just adds one more ingredient to the nebular theory, and together the nebular and the condensation theories fully account for our understanding of the formation of the solar system. So what does the condensation theory say? The condensation theory says that uh, there is there is dust. It basically emphasizes the role of dust in the cloud, so which had not been taken seriously before. So our original nebular cloud has a lot of dust in it, right? And the dust plays a very crucial role, which was not considered in the original nebular theory. In fact, the dust plays one of the most important roles in the formation of the planets. So what role does this dust play? So we knew that there was dust. Our cloud was just made of gas and dust. But what role does this dust play? Well, for that, you have to understand condensation. And let me just quickly explain condensation on the Earth, and then we'll come back to the formation of the solar system. So what does the word condensation mean? Do any of you know what condensation means? So condensation is when you have liquid in the form of gas, most likely water, and it comes into contact with something cold and forms droplets of water. So that's condensation. So, for example, suppose you have water vapor in the air, right? And then the temperature becomes really low. Or let's just think about clouds. So you have water vapor in the atmosphere, right? Water vapor is just water in the form of a gas, just water molecules flying around. And when the temperature is really low, what happens is that the water vapor forms, the water molecules sort of clump together and form droplets of water. So if you just have water molecules flying around like this, that is water vapor. But when the water molecules sort of clump together, then we consider then it's in the liquid phase, and then we say that this is a tiny drop of water, right? So the difference between a tiny drop of water floating in the air and water vapor is that water vapor is just molecules of water floating around, whereas uh, liquid water is a very large aggregation of molecules which are all sticking together, right? Now the thing is that if you just have water vapor, which is water molecules flying around, they will not just stick together and form a droplet of water. They're not going to do that. So if you just have water vapor, even if you lower the temperature a lot, it will not form droplets of water. So what do you need in order for it to form droplets of water? What you need is some kind of a dust grain. So a dust grain is typically much larger than a water molecule. So I'm just drawing it like a big blob over here. So if you have a dust grain, then that is going to speed up the formation of liquid water. So how is that going to happen? The dust grain provides a site where water molecules can stick to. So if you have all these water molecules flying around, they'll see the dust grain and they might just stick onto the dust grain. So a bunch of water molecules might aggregate on the dust grain. So the dust grain becomes like a hangout place where all the water molecules can go and sort of stick to. And so because of this dust grain, more and more water molecules will aggregate on the dust grain. And so you have a large collection of water molecules, which you would not have had you not had that dust grain to start with. So when you have dust grains, it's very easy for water vapor to form droplets of water, tiny droplets of water. And that process is called condensation. So the dust grain, um, so the dust grain facilitates condensation. And so if you have a lot of dust in the atmosphere, you get more droplets of water. This is and these droplets of water in the sky are what we call clouds, right? Now, this does not necessarily have to happen up in the sky. This can also happen at ground level. So you might find that on cold days there's a lot of fog in places which have a lot of pollution. Why does that fog happen? So in the morning, if the temperature is low, if it's really cold from the night before, then the water vapor in the atmosphere can start condensing on the pollution particles, which is basically just dust in the atmosphere. And so you have lots of droplets of water in the atmosphere, and we perceive that as fog. So the more pollution you have, the more fog you have in the atmosphere. So anyway, so the point here is that if you have dust present, then then the dust particles allow the gas molecules to sort of aggregate and condense, right? The same thing is believed to have happened in our nebula that we were talking about earlier. So in the nebula, you had a lot of gas and then you also had a lot of dust, right? So the dust played the crucial role of acting as a site where the gas molecules could condense. So interstellar dust, which are basically tiny grains of rocky, icy or rocky material scattered through space, facilitate the condensation process. And as a result of that, you have clumps forming in the gas, right? So if you did not have all this dust in the atmosphere, in the nebula, then then the gas would not have clumped. It would just have remained as gas. So the dust grains act as condensation nuclei, and they speed up the process of collecting matter. And it's very similar to the way raindrops form in the atmosphere, or clouds form in the atmosphere, as we just discussed. All right. So these clumps which start forming on these dust grains are initially very small, but they grow larger with time, right? So you might have a dust grain over here, and then the gas molecules start aggregating on this dust grain. The gas molecules are way smaller than the dust grain, so this diagram is not to scale. And then more gas molecules aggregate, more gas molecules aggregate, and so you end up with a clump of the gas, which at that point the gas might turn into a solid or a liquid. So it would be a droplet of, or it would be a speck of solid matter at that point. So the dust allows this clumping process to happen, right? And these clumps gradually grow larger with time. So the gradual growth of the clumps is called accretion. So what is accretion? So at first you start out with a bunch of clumps, right? And then these clumps, so you can think of these clumps as these tiny solid, tiny chunks of solid matter, which have formed as a result of the gas forming clumps. And so these clumps might collide with one another. And if they collide, they might stick together, right? And so you have a bigger clump. And so that bigger clump might slam into some other clump, and the other clump might just break off. Part of it might just break off and the other part might stick. So basically these clumps are always colliding with each other, and they might start getting bigger as they aggregate with each other, right? In the process of colliding. So this gradual growth of the clumps by collision and sticking is called accretion. So you started out with very small clumps in the beginning, but they're constantly colliding with each other. Sometimes they're sticking together, sometimes they're just breaking apart. And so the clumps will just keep on getting larger and larger as they keep on colliding with each other. So this gradual process of growth is called accretion. And simulations show that in 100,000 years, which is really a very short time on cosmic timescales, in only 100,000 years, accretion can produce objects which are quite large, about 100 kilometers across. And so you have these large masses which form as a result of these small clumps colliding and sticking together and getting bigger, going through more collisions, getting even bigger. And so you end up with these large solid objects, which are now called planetesimals. So in 100,000 years, you would end up with a bunch of planetesimals which are or orbiting the center of the cloud. So you at first you just had a cloud of gas, but then as a result of condensation and accretion, you end up with a bunch of planetesimals. And so at that point, the cloud kind of looks like this, like in this picture. So you can see that there's a lot of gas and dust. You can see the center of the cloud is very, very hot. And you have these chunks of matter, which are which could be the planetesimals, right? The largest ones would be called the planetesimals. The other ones would just be flying rocks. All right. So the planetesimals would, now all of these planetesimals would have different compositions. So uh, they would not have the same composition. They would be made of different materials depending on where they formed. And so I want all of you to understand this part. Why would the planetesimals be made of different materials? Because they're forming through the same process, but so why would they be made of different materials? So that's what I'm going to explain next. So basically, there are four types of materials which might have formed in the early solar system. You could have had metals, rocks, hydrogen compounds, and light gases. So these materials would be formed by condensation at different places in the solar nebula, depending on their distance from the center of the nebula. Remember that the sun is forming at the center of the nebula, right? And so the composition of the different materials, the different planetesimals would depend on where the planetesimal was formed. So let me just explain this. So let's say this is the center of the nebula where the sun is forming. And this is, let's say a planetesimal is formed over here at the same distance where the planet Mercury is, right? So over here, it's very, very hot, right? Because you're pretty close to the sun. So only the sturdiest materials would condense out over here. So the kind of materials that can condense out at these distances is usually metals. Metals are very sturdy. So a planetesimal that's formed somewhere over here would be mostly made up of metals, right? Uh, a little further out, let's say at the distance of the Earth, it's much cooler, right? And so cooler than the first location, because you're further away from the sun. So over here, the type of planetesimal that would be formed would be made up of materials which are not as sturdy as metals, but still quite sturdy. So those are the rocky materials. So a planetesimal which was formed at the distance of the Earth or Mars, for instance, would be mostly made of rocky materials, right? And then as you go further out, you would have planetesimals which are made of ice, because it's very cold outside, like as you go further away from the center of the nebula. So you can easily have planetesimals which are formed out of ice. So the point is that depending on where you are, um, you can see over here in this graph, in the hottest regions which are closest to the sun, only the metallic grains could form. So only the metals could condense out in places which are very close to the sun. And then a little further out, about 1 astronomical unit from the sun, rocky materials would condense out. And what I mean by rocky materials, the technical term is oxides of silicon, iron, or magnesium. These kinds of things could form at a distance of 1 astronomical unit from the sun. At a distance of 3 to 4 astronomical units, you could have water ice. So you would have materials made up of water ice at a distance of 3 to 4 astronomical units. And at a distance of more than 5 astronomical units, you can have uh, materials which are made of ammonia and methane ice, because these can only exist at very low temperatures, right? So depending on the temperature, or in other words, the temperature of a certain location determines what kind of materials would condense out over there. And that determines what kind of planetesimals would be formed over there. And so that explains why Mercury, the planet Mercury, is mostly made up of metal, because Mercury formed very close to the sun, and so uh, Mercury is mostly made up of metal. And then Earth and Mars formed sufficiently far away from the sun that they are mostly made up of rocky materials. And so the Earth is so much rock and a little bit of metal. And then as you go further out, very far away, you see objects which are mostly made up of water ice or ammonia ice. That makes sense? So that is why the solar system is differentiated. You have different planets made up of different materials, and now hopefully you understand why that is the case. So the planets, the formation of the planets began with condensation, right? And I explained what condensation is, and I also explained that the type of material that condenses depends on the distance from the center from the sun. And so that is why you get different materials condensing out at different distances. All right. Okay. Now, why do we have the asteroid belt and the Kuiper belt? So we understand why how the planets formed, but why do we have an asteroid belt or the Kuiper belt? So basically, once the planets started forming, so at first you had something like this. You had the sun, and then you might have had several planetesimals, say at the orbit of Mercury, the distance at which Mercury orbits, you might have had several planetesimals orbiting at that distance. So what would happen is that these planetesimals would keep colliding with each other, right? Every time you had a collision, the two planetesimals that are colliding might just stick together, or one of them might just get completely shattered and destroyed, or both of these might happen. Like one of them might get completely shattered and one part of it might stick, right? The other part of it gets destroyed, and so on. So these planetesimals always keep colliding with one another. And uh, another thing that might also happen when they collide with one another is that suppose these two collide somehow, and so one of these might just be kicked out of this orbit. So one of these might just be knocked out of this orbit. So the result is that as these planetesimals keep on fighting with each other, um, eventually one of them will win out, because all the others just get either absorbed or kicked out of orbit or just turned into dust, right? So eventually you're just going to end up with one planetesimal, and that will become the planet Mercury. So all of these will eventually be kicked out or destroyed, and there will just be one planet left, and that becomes the planet Mercury, the only one that's surviving. I was mentioning in the last class that all the planets are basically the last man surviving in their respective orbits. And so that is how you end up with one single planet at a given orbit, because we say that that planet has cleared out its neighborhood, as I explained in the last class. So now what happens to the planets or the planetesimals that got kicked out of orbit? So a planetesimal that got kicked out of this orbit might end up somewhere over here near the orbit of Venus. And this is Venus, proto-Venus, early Venus. And so then this planetesimal has to now deal with Venus, and it might either get kicked out of this orbit as well, or it might get absorbed into Venus, or it might be shattered into dust. Something like that might happen. So basically, Venus will also clear out its neighborhood. This is Mercury, this is Venus, and then Earth also did the same thing. So all of these planetesimals that were kicked out of the orbits of the three inner planets ended up in in what is called the asteroid belt. So the asteroid belt, as you know, so you have Mercury, Venus, and then you've got Earth orbiting the sun over here, and then you've got Mars orbiting the sun over here. So in between Mars and Jupiter, there's a large region of asteroids, as we've discussed, orbiting the sun. So where did these asteroids come from? So these asteroids were the ones that were just kicked out of the orbits of the inner planets, and they just ended up in the asteroid belt. So the asteroid belt is where they all ended up, and that's why you have an asteroid belt, right? Okay, and it's the same thing that happened with the Kuiper belt. So the Kuiper belt is a large collection of icy objects which are orbiting beyond the orbit of Neptune. And the reason that they exist over there is that they've been all kicked out of the orbits of the outer planets, and they just ended up in the Kuiper belt. So that's why you've got an asteroid belt and a Kuiper belt. Okay, now, so we've come a long way. We've seen that we started with a huge cloud, which is called the nebula. And then the nebula started contracting, became unstable and started contracting. I'm just recapitulating all the things that happened. And then as it contracted, it started spinning and assumed a flattened shape. So I should say that as it contracted, it started spinning faster than it was spinning before, and it started getting flatter so that it looks like a pancake that's rotating rapidly. And the central part of that rapidly rotating cloud, a flat cloud, became the sun. The other parts of it turned into the planets and the asteroids and the comets. And then so everything was so that's how things were at that point. Um, then something happened with the sun. So once the sun was born, so the sun is at the center of the nebula right now. So once the sun is born, when stars are born, what they do is they go through a phase called the T Tauri phase. So what's meant by that is that the stars give off tremendous amounts of radiation and solar wind. So the sun always puts out radiation and a stream of particles, which is called the solar wind. These particles are mostly protons and electrons, which always come out of the sun. So when stars are born, they put out tremendous amounts of solar wind for a short amount of time. So the sun, when it was going through its T Tauri phase, and that phase is called the T Tauri phase, it doesn't last for very long, but all young stars go through that T Tauri phase. So when the sun was going through its T Tauri phase, what it did was it put out these tremendous amounts of solar wind, and as a result of that, whatever remnants of the original nebula, primordial cloud were left, they were just kicked out. And so then all we were left with was the sun and the planets and all the asteroids and comets that formed. And that was how the solar system came into existence. All right. So that is a brief history of the solar system. Does anybody have any questions? So I've given you some links over here if you want to see this same thing in videos or computer simulations. So these links are very nice if you want to learn more about the history of the solar system. But basically, that is our understanding of how the solar system came into existence. That's the history of the solar system. So all the planets formed roughly at the same time, um, and it all started with a primordial cloud of dust and gas.